Will a black hole destroy the Earth? It's a question everyone asks when they find out about black holes. The short and simple answer is probably not, because the closest black hole that we know of is located about 3,000 light years away. This black hole is called V616 Monocerotis, or V616 Mon for short. As I mentioned, V616 Mon is located about 3,000 light years away and has between 9 to 13 times the mass of the Sun. The only reason we know a black hole is there is because it's located in a binary system with a star with about half the mass of the Sun. The only thing small and heavy enough to make this star move like it does is a black hole, and without this star we wouldn't know about V616 Mon because we can't actually see black holes. They're black. We can only see their gravitational effects on other objects such as this star. One of the most famous black holes, Sagittarius A star, was discovered the same way. Since the start of the century for over 16 years now, some astronomers have been observing certain stars near the centre of the Milky Way using infrared telescopes in order to see past the dust. They watched the movement of these stars and found they seemed to have slingshot orbits around something that wasn't there. The astronomers concluded that these stars were orbiting a black hole, because that's the only thing small and heavy enough to cause these stars to act like they do. This black hole was of course named Sagittarius A star, or Sag A star for short, and is the supermassive black hole in the centre of the Milky Way. The second closest black hole to Earth is Cygnus X1, which is located 6,000 light years away and has 15 times the mass of the Sun. Unsurprisingly, it's located in a binary system like V616 Mon. The third closest black hole is also in a binary system. Someone with no knowledge about this topic might say that it must be that black holes are just usually in a binary system, but this is absolutely not the case. In reality, all of these black holes we have discovered have something nearby them because that's the only way we can detect them. Or it's one of the only ways. One of the coolest ways to discover black holes is by detecting gravitational waves. Einstein predicted the existence of gravitational waves in 1916 based on his theory of general relativity. And then on the 14th of September 2015, LIGO, or Laser Interferometer Gravitational Wave Observatory, detected gravitational waves for the first time. Later on the 4th of January 2017, this year, LIGO have detected gravitational waves for the third official time. If you want to know more about this, check my video on the third gravitational wave after watching this one. There are two different types of black holes, and I've mentioned examples of each type. V616 Mon and Cygnus X1 are examples of stellar black holes created when a massive star collapses. The other type of black hole is a supermassive black hole. These black holes are located in the centre of most galaxies, including our galaxy. Sagittarius A star is the Milky Way supermassive black hole. We don't know exactly how supermassive black holes form, but we do have theories. On my other video of how we may have a picture of a black hole soon, Robert Lorison commented and proposed a theory of how supermassive black holes form. He basically said that the first massive stars exploded in a hypernova, leaving a stellar black hole behind, which, as he said, served as the starting point for a galaxy to eventually form around it. It's very possible, but we just need more evidence for it, so we can confidently say, yes, this happened. There is another type. Miniature black holes are black holes that would have a mass much smaller than the Sun's mass, but we've never seen this type of black hole. V616 Mon is the closest black hole that we know of, but honestly there are most likely black holes closer than V616 Mon because we can't actually see black holes, and it's important to make that clear. Black holes don't emit any radiation because they're so gravitationally strong. Light, the fastest thing in the universe, can't even escape it. Sometimes we can see the shadow the black hole causes onto the bright matter zipping around it. When matter falls over the event horizon, it lets out radiation, which is why rims of black holes tend to be extremely bright. But why are they so bright? Not just black holes, quasars as well. How can they be so bright when black holes don't let anything escape, or more specifically don't let any radiation escape? Well, it all comes down to the matter orbiting and falling into the black hole. Imagine placing each end of a rubber band to two different cars, and then driving these two cars in the same direction. If the cars are going at the same speed, there's no problem. But if the front car suddenly starts going faster, let's say 20 miles per hour, while the car behind is going 10 miles per hour, the rubber band is inevitably going to reach its stretching point and snap. This is what happens to objects when they approach a black hole and is called spaghettification. The side closest to the black hole is being pulled faster than the far side of the object. And this is also true for material orbiting the black hole, not just heading straight into the black hole, because the near side of the object will be orbiting faster than the outside, forcing it into a spiral. Both scenarios, when material is spaghettified, create so much friction that it can heat the particles hotter than most stars. And since there's usually a lot of material orbiting a black hole or an accretion disk, there's a lot of fuel to keep it shining. For all we know, there could be a black hole heading straight for our solar system, or worse, Earth. But even if a black hole did get close to our solar system, it would be pretty obvious because we would start to see the effects. But let's say a black hole was heading straight for our solar system. If we could, we would want to kill it, right? But how do you kill a black hole? Well, according to Stephen Hawking, black holes can actually evaporate, but over a very, very long period of time. All around us, virtual particles are constantly popping into existence. It's often said that they come in pairs, a particle and an antiparticle. After existing for an extremely short amount of time, the two particles recombine and annihilate each other. Now, if you have one of these particle pairs pop into existence at the event horizon, one particle will fall into the black hole, but the other particle is able to escape into space and become an actual particle. And when particles escape, the black hole loses a small amount of its energy and therefore some of its mass, because mass and energy are related by Einstein's equation E equals mc squared. This is called Hawking radiation. So, by these virtual particles popping into existence at the event horizon, the black hole will eventually evaporate into nothing, but after an extremely long time. So it turns out all we need to do to defeat a black hole is to wait it out. But aside from Hawking radiation, is it possible to destroy a black hole? For instance, what if we detonate a nuclear bomb near the black hole or inside the event horizon? Or instead, how about we shoot bullets at the black hole, or even lasers? What if we sent a star into the black hole? How about we construct a black hole out of antimatter somehow? Would that destroy the black hole? No. Sending any matter into a black hole just adds to its mass and makes the black hole larger, whether it's a nuclear bomb, bullets, lasers, a star, or even another black hole. At the moment, it seems that waiting eons is the only way to destroy a black hole. Comment any ideas in the comment section on how to kill a black hole. Make sure you subscribe for more content on astronomy and futurism. If you enjoyed this video, check out my most recent video or my playlist on black holes. Thank you so much for watching. Have a nice day.